We hear so much about these incredible AI models like Gemini or ChatGPT. But what about the actual physical hardware that makes it all possible? Well, today we're going to pull back the curtain on the specialized chips that power Google's AI, and we'll do it through the eyes of one of its top architects, Jeff Dean. It's a story about a crisis, a huge invention, and a really bold vision for the future. So where does a story like this even begin? It all started back in 2013 with this quote from Jeff Dean. He could see just how powerful deep learning was becoming, but when he actually did the math on what it would take to bring that power to everyone, well, the numbers were, as he put it, scary. And this wasn't some minor hiccup. This was a potential showstopper.
Just how scary are we talking? Well, get this. To roll out just a single better speech recognition model to all their users, Google would have had to literally double its entire fleet of computers around the world. I mean, just pause and think about that. One new feature would mean doubling a company the size of Google. Right then, they knew they couldn't just keep buying more computers. They had to invent a whole new kind of computer.
And that simple but terrifying math problem is our first major topic. This wasn't just some boring spreadsheet. This scary calculation was the spark that kicked off a whole decade of incredible hardware innovation.
What's just wild here is the speed. The problem was spotted in 2013, right? And just 2 years later, in 2015, the very first Tensor processing unit, or TPU, was physically up and running in Google's data centers. That's an unbelievably fast turnaround. And today, they're on their 7th generation of these things, building what are basically AI supercomputers.
So, did it actually solve the problem? Oh, absolutely. The performance jump was just staggering. The first TPU wasn't just a little bit better. It was 15 to 30 times faster than the CPUs and GPUs they were using at the time, and maybe even more important, it was 30 to 70 times more energy efficient. So they didn't just solve their problem, they completely changed the game.
Okay, so let's move on to the next piece of the puzzle. Because look, building a crazy fast chip is one thing, but the real genius here, the secret sauce, is the philosophy behind it. This is where hardware meets software.
It all comes down to this idea called co-design. And this is way more than just having hardware and software engineers talking to each other. As Dean explains it, it's about the hardware team trying to skate to where the puck is going. They're trying to predict what kind of wild AI models researchers will want to build 3, 4, even 6 years from now. And then they build the chips of today to support the software of tomorrow.
And this creates this amazing flywheel effect, right? First, the researchers make these forecasts about where AI is headed. Then, the hardware team builds chips with specific features tailor-made for those future ideas. And what's the result? Well, groundbreaking models like the Transformer, which is the engine behind so much of today's AI, suddenly emerge and find that the perfect hardware is already sitting there waiting for them, ready to unlock their full power. All right, so Google builds this incredible, world-beating advantage for itself. But the story doesn't just stop there. Let's talk about how this insane technology went from being a secret weapon inside Google to a tool for the rest of the world. This all leads to a really big question. Are we at a tipping point? A moment where everyone else can finally get their hands on the kind of computing power that used to be exclusive to a place like Google? Well, according to Dean, the answer is a big yes, and it's mostly because of the cloud. But how do you make a supercomputer easy for anyone to use? You can't just throw the hardware out there. You have to build this amazing software layer on top of it. Think of it like this. There's a tool called XLA that's like a universal translator, making sure any code runs super efficiently on these custom TPU chips. Then you have frameworks like JAX, which is the user-friendly toolkit researchers love. And then you have the master coordinator, Pathways. And Pathways is where the real magic happens. It's a system that, as Dean perfectly puts it, gives the illusion of a single system image. So what on earth does that mean? It means a researcher can write code like they're just running it on their own laptop. But behind the scenes, Pathways is splitting up that work across up to 20,000 different chips, sometimes in different cities, and making it all feel like one single, ridiculously powerful computer. So we've got the hardware, and we've got the software that makes it all sing. But where do the actual ideas come from in the first place? This brings us to a topic that Dean is really passionate about: the need to power future breakthroughs by investing in fundamental research. Yeah, this is a point he really hammers home: the absolute need for a vibrant academic research ecosystem. He makes the case that it's the early-stage, creative, often publicly funded ideas from universities and labs that eventually lead to the massive breakthroughs that companies like Google can then build on top of. And for him, this isn't just a theory. I mean, Google itself is the ultimate proof. The company was literally built on the shoulders of academic giants. The core technologies of the internet, the processors in our computers, these things came out of that ecosystem. Even the fundamental ideas behind neural networks, the very engine of modern AI, were born in academic labs decades ago.
Which brings us to our final section. With all this mind-bending power at our fingertips, what's the ultimate goal? What are the grand challenges we should be pointing this stuff at? For Jeff Dean, one area rises above the rest, what he calls AI's healthcare moonshot.
This right here is the vision. This is the why behind all the silicon and all the code. He asks this simple but incredibly profound question. How can we use every past decision that's been made in health to inform every future decision? It's just a huge, ambitious goal. To build a global, learning healthcare system where tech helps every single doctor and patient make a better decision.
Now, of course, a goal that big is a moonshot for a reason. It comes with massive hurdles. On the technical side, you've got these huge problems, like how do you train AI on sensitive patient data without ever compromising privacy? And then on the logistical side, you have the messy real world of data being stored in a million different ways, all tangled up in complex legal and regulatory webs. And this really gets to the heart of it. Solving a challenge this huge isn't just a machine learning problem. It's going to take an equal partnership between the ML experts, the systems builders who can create these massive platforms, and crucially, the policy and legal experts who know how to navigate the complex human side of it all. No single group can do this alone. So we're left with this really powerful idea. We've journeyed all the way from a scary calculation on the back of an envelope to building AI supercomputers to now aiming that power at one of humanity's biggest challenges. So if health is AI's current moonshot, the question to leave you with is, what should be next?